All right, so I'm Andy Honig. I'm from Google, and I'm going to talk about KVM security improvements. So a little bit about why I'm here and why I care. So I'm the tech lead on the cloud security team for Google. And for anyone who doesn't know, we have a product called Google Compute Engine. And from my point of view, that's lots of untrusted users who I'm really scared of that can run whatever code they want inside of VMs on the same infrastructure that runs search and Gmail and everything else. So for Google, I would say that security is probably the #1 priority for KVM. It's the killer feature. Otherwise, we could just sell people Docker containers or just let them run Linux processors. So the main thing that VMs actually provide us is that isolation. And all of our VMs are on KVM. We've done a lot of work on KVM. We've had 9 CVEs that are guest-facing. I like to distinguish the guest-facing ones versus the host-facing ones, because those are the only ones that really scare me, because those are where I have untrusted people. I also did a lot of work in VMware before KVM and had a bunch of VM escapes there. So I've been trying to break out of VMs for almost 10 years now. So I want to talk about how we think about vulnerabilities in KVM. And there's lots of different types, and this list gets even bigger when you think about nested virtualization, what you can break into from something else, what are those security boundaries and what do they mean. Obviously, the #1 priority is guest execution escape. That's where a VM gets to run code on the host. We can't have that. The second one, which is almost as bad, is where the guest gets to read other guests' data or host data. Obviously, that doesn't fly very well on a cloud provider. Guest denial of service of host, we put that third. Other people might put it further down because it's denial of service. But we have a pretty big service. We have a lot of different users. And if a small number of them can take down the whole service, someone will. You know, there's not a lot of money made in being an asshat, but people do it. And we see it a lot at Google. So we have to be somewhat aware of that. And then there's sort of ring escalation attacks. There's the host ring 3 to host ring 0 vulnerabilities. Those are things in like the ioctls that allow someone on the host to get into root because of KVM. And then there's the guest ring 3, ring 0 vulnerabilities, where someone in the guest in ring 3 can break into ring 0 in the guest because of something KVM does. And then there's sort of ring 3 denial of service attacks, which I care the least about. So I put 3 of them in red because the other 2 and all the others are kind of general Linux problems that get a certain amount of attention, and we obviously want to avoid those. Whereas the first 3 are very unique to KVM and very unique to virtualization. And from my point of view as a cloud provider, they're the only ones that are at a direct attack point from someone who's bad. So what do we do to secure this? So code review sounds simple. Obviously, every commit that goes into Linux is already getting reviewed by at least 2 people, usually well more. We run our code reviews for security a little bit differently. Rather than looking at commits as they go in, we find that a lot of vulnerabilities are from code that makes sense when it's put in, but then gets changed. Then something else that it relies on gets changed, and there's these interdependencies. Also, people are generally looking for correctness issues or performance issues or style issues, where it's nice to have a specific review just for security. So we're several versions behind the head branch, the upstream. So every time that we snap forward to a new branch, we dedicate the 2 or 3 weeks or whatever really it takes. And we sit and we do a thorough security review, and we look through things that we know are particularly complex or guess complicated. Then we do security testing and fuzzing. So about half of the vulnerabilities we found are via fuzzing. So what we did when we did our first code review, we looked at all of the things that we consider to be attack surfaces that are things that do something in response to guest input. So there's the device emulation that's in KVM. That's the APIC, the IOAPIC, the PIT, and the PIC. Those are accessed via IO and MMIO ports. So we wrote a fuzzer that goes through the IO and the MMIO ports supported by KVM and hammers them with random data from multiple processors from multiple modes while switching modes and not changing pages and all those other fancy things. There's the MSR space. Obviously, most of those are emulating real hardware, but some of those are just power virtualization interfaces. So we have something that hammers on those. We try to give it somewhat normal data, something close to valid, not entirely random, but sometimes we go with entirely random. There's the emulator. So we've done we feed it random instructions, and we're not quite as cool as the Technion work because we don't actually verify that it does the right thing. We just verify that it doesn't crash, right? Because we're looking for security problems, so we're just looking for crashes. It would probably be a little cooler if we were doing what they were doing, which is looking for where the actual behavior is incorrect. But from a security point of view, we don't actually care. So I don't actually care if KVM works. I mean, I kind of care. I don't want to break it. But it's my job to make sure it's safe. And then the third step, which is what I'm going to talk most about today, is about attack surface reduction. So we try to take, all right, so we have this large list of things that could potentially be vulnerable. And we're emulating lots of complicated behavior. How can we sort of bring that down to make it a little bit safer? I will say that I'm only really focused on x86. I've never even looked at the other code, so if I say something that sounds stupid or doesn't apply, that's probably why. I'm sure the other architectures are important, they're just not important for Google right now. So I'm going to talk about where some of the vulnerabilities that we found in the past were, just sort of to sort of introduce where we're going. The first one was in the time emulation MSR. It was an out-of-bounds write to an atomic page. So there was a function gfn to page that essentially takes a guest address and it converts that into something, a host virtual address that can be written to. The problem with that function was that it validated just one address. So it doesn't actually validate a range of addresses, and obviously you're not going to memcopy 1 byte. In this case, you were memcopying 32 bytes. So the first byte was checked to make sure it was a valid guest physical address. None of the other bytes were checked. So if the guest gave you an address that was at the very end of guest memory or at the very end before a memory hole, you would go ahead and do a memcopy onto host allocated buffers. So one of the reasons why this, we try to look back and think about what caused that vulnerability, or where did the developer mistake happen, or what happened that made it harder. So there's a couple things that were sort of caused this, in my opinion. One, the check was very far away from the actual usage. So for performance reasons, the actual check was done when the guest programmed it, and then the actual write was done much later on enter and entrances to guests after a scheduling event. So the check is sort of both earlier in time mentally and also very far away in code. So to prevent that, that was actually the cause of another bug as well, that same pattern, but that pattern's kind of been removed, and now there's the cached. That was a performance improvement, and now there's a GFN cached struct that makes it impossible to sort of make that mistake and lets you use that same performance improvement. There's another bug in the IOAPIC. It allowed you to read pretty much arbitrary host memory. There's this IO reg select in the IOAPIC. So the way you read and write to the IOAPIC is you set the IO reg select, and then you do a read or write, and that says where you really meant to read or write. That was sort of because there was a limited amount of hardware back when Intel first designed this. Obviously, it doesn't really make a lot of sense now. So it would take the IO reg select, which is a guest provided value. It would do some calculations on it. It would make sure it's within the redirection table with an assert, and then it would dereference, use that as an index to an array. The problem is that the assert doesn't do anything except in debug builds, so the guest can sort of read everywhere. After that, we just did an audit of every assert in KVM, and that's something that's now on our checklist every time we snap forward to a new version. So another recent one, this was a problem in the emulator. It was improper emulation of the push A instruction. I didn't actually put the code up here because the code path to actually make this happen is really, really complicated. What ends up happening is you end up in a loop between the kernel and user space. And while in that loop, you go on forever while incrementing a pointer forward, and eventually you do a memcopy of null. What are the conditions that actually trigger it are, it's when the guest does a push A and the stack starts in MMIO memory but finishes in regular RAM. So no reasonable OS would ever do that. And actually in the fix for this, we didn't actually make that work correctly, it just doesn't crash. If someone needs that feature, you're wrong, please don't do it. We actually were able to prove that a VM escape was possible, although it was pretty complicated in this one. While you end up always memcopying null eventually, while it's sort of incrementing one by one, you can race it with another CPU and cause it to bring down the VM, which will cause it to drain the asynchronous page fault handlers, which are overridden. They're the asynchronous page fault work items. So where were those three vulnerabilities? One was in the MSR handling, one was in the IOAPIC, and one was in the instruction emulator. So in general, let's look a little bit more. So this is 2 years worth of data. I looked at all of the guest-facing bugs that fit into one of the first 3 categories, and I sort of said, where are they? So 6 of them were in device emulation of some sort, 2 were in the instruction emulator, and then 2 were in MSR emulation. So the first question is, all right, how much of those things really need to be there? So some other things that we looked at that actually don't show up here, the MMU, which is something that to me looks extremely complicated. We've never found a bug in it, and it's not from not trying. So we don't really consider that as something we need to reduce. We kind of want to reduce the attack surface of things where we found bugs because we think that's where there's going to be bugs in the future. So what we would like to, you can't really get rid of all those features, right? You have to emulate the MSRs that need to be emulated. You have to emulate the old school IOAPIC and the PIT and the PIC. OSs won't boot up without it. But a lot of those things don't need to be in the kernel. So a lot of those things were moved in the kernel for performance reasons, or were just originally done in the kernel for reasons I don't know. But a lot of them can be moved. Why is it better to be in user space? A couple reasons. One, it's much harder to exploit a vulnerability in user space in general. There's ASLR, and I realize there's kernel ASLR now as well, but it's much more pervasive in user space. It has more bits of entropy. It's less likely to have a leak because it's per process as opposed to one large address space where you can play cache attacks and games like that. As well as you got stack canaries and app armor, and a lot of other mitigations in user space that just aren't available in the kernel. Also, if someone does do an escape, it's not as big of a problem. If someone breaks into user space on a Google production machine, obviously that's a disaster. That's bad, but it's certainly not as bad as them breaking into the kernel. The last one, denial of service bugs, which are something that we do have to worry about, become a non-issue. If you can crash your own VMM, ooh. Another point that I comment here, we're pretty early in experimentation, so if you want to correct me and call me stupid, please do so. I'm sure we're doing all kinds of things wrong, but so far it's looking pretty good. So what do we want to do? Basically, we want an opt-in way for the user space VMM to push a lot more functionality in user space. And so what we're doing first is we create a mental model like, all right, let's just move everything in user space and that was on that attack surface list. And then from a performance problem, that's not great. So some of those things need to be done pretty fast. And then let's add some functionality into cherry pick very small things back into the kernel. So rather than the entire APIC, for example, being in the kernel, just cherry pick the things that actually need to be performance critical in there. Sort of the goal that we're targeting is we want a 50% attack surface reduction with 0.1% perf impact. I'm careful to say on macro benchmarks for modern guests on modern hardware. So obviously someone's going to come in and say, well, you know, this combination of instruction emulation is slower with this device that does this. And yeah, that might be true. But when I say macro benchmarks, I mean network throughput, network latency, disk throughput, disk latency, and then some sort of heavy compute workload. So I think we can keep it below 0.1 for all of those benchmarks. And you know, Google's going to keep me honest because if it's not close to that, they're not going to let me put it in. And then so modern guests that rely on old school PICs or hammer on the IOAPIC a lot, things that don't use X2 APIC. Those guests are old. They're still going to work, but they're going to be a little bit slower. If you care about performance, you're probably on a modern OS. LS have supported X2 APIC for almost 10 years now. And then modern hardware, that one's a little bit grayer. We're probably targeting Ivy Bridge for our internal usage, just because that's where we're going, and that has most of what I'm making slow hardware support for. So most of what I'm actually making slow by moving to user space, there's hardware support for it in the hardware, which is even better. I get this question a lot. You know, you want to remove attack surface and you want to measure it. How are you going to measure it? There's sort of 2 metrics, and we'd like to be greater than 50% on both of them. One is the lines of code that process guest input. So that kind of, we just go through the code and we kind of eyeball it. Does that process guest input? We've talked about automating it by having a guest that does very little and then seeing what lines are covered in KVM, and then having a guest that does a lot and seeing what lines are covered and having some sort of automated fancy attack surface measurement framework, but then we figured that was too much work and we just counted them. The other metric that I like is the number of pages of Intel manual that are emulated. Just because that's a pretty good measure of complexity, right? We want to take, it's not just lines of code that we really care about, right? We want to take things that are complicated, things that are difficult, and we want to move them from the kernel to user space. I've seen people use the number of mem copies and array dereferences as well. just because those tend to be where security vulnerabilities are as well. So I'll talk a little about sort of, this is the current world of KVM. There's the fast approach, which is sort of the common approach, where disk networking in most devices are in user space. And then in KVM, there's 4 things. Well, there's lots of things, but there's 4 things that I notice and note. There's the PIC, which is the old school programmable interrupt controller. OSs use it for about a millisecond, and then they move off of it. There's the APIC, which is still used a lot. There's the IOAPIC, which is not really performance critical, but it's still used by guests a lot. Faster things will use MSI or something better. And then there's the x86 emulator. And then at the bottom, you actually have virtual APIC that's done by the hardware. So starting, well, I don't know when it started, but so the TPR support was the first thing that was sort of, and I want to draw a parallel between what I'm trying to do between user space and the kernel to what Intel does in the hardware. So Intel wanted to make virtualization faster, and there were some parts of the APIC that needed to be faster for virtualization. So they didn't build an entire virtual APIC in the hardware, and that was mostly for silicon reasons. But so they sort of cherry-picked the few things that really could make a difference for virtualization performance by moving them into the hardware. And the first one was TPR virtualization, and now there's EOI virtualization and self-IPI virtualization. And those are actually done in the hardware. But I want to highlight that they didn't take the entire APIC and make it hardware supported inside the VM. They just took a couple things and cherry-picked them. And even from that point of view, even things like the TPR virtualization, they didn't fully say TPR accesses won't exit. They said TPR accesses that are done with a move, that are aligned, are going to not exit. So if somebody does an exchange add to the TPR, it's still going to exit because Intel didn't want to implement that. And somebody might do that, but that should work, but it doesn't need to be fast. Another approach, which is much less common these days, which I would like because I'm a security guy and I don't care about anything else, but it's really, really slow. So you can actually take all of the interrupt, the IRQ chip, and leave it in user space. I don't know how many people do that today. I don't see a lot of development or work on it. It's safer, right? You've taken some attack surface and you've moved it to user space, but it's much, much slower. It doesn't enable any of the hardware support, which is kind of a problem. Our measurements on Windows is it takes about triple as long to boot, 2.5 times to 3 times as long. So that's probably not going to fly. So what we're building is I'd like my cake and I want to eat it too. So I'd like it to be fast and I'd like it to be safe. So what we're building is we've taken the PIC, the APIC, the IOAPIC. We haven't done the instruction emulator yet, but that's what we're working on. And we've moved them into user space. And then we take very limited features and we move them and we cherry pick those back into the kernel. And most importantly, we turn back on all the hardware supported features. So the hardware supported TPR virtualization, the hardware supported EOIs, the hardware supported self-IPIs get turned back on, but everything else is in user space. So, what we've been measuring, what really does need to be in the kernel of the APIC, right? If we put all of the APIC back in, or if we put everything that I took out back in because it's performance critical, we really haven't won anything. So what actually needs to be, we've noticed that EOIs, TPR adjustments, and self-IPIs definitely need to be in the kernel. Non-self-IPIs, maybe. We're really not there yet. We haven't measured it. But if we need it to get to our 0.1%, we'll put it back. But we're not going to put it back for using the xadd instruction to do it. It's going to be if you're using x2 APIC and you write to the MSR, right? That's the only thing that really needs to be fast is the right way to do it. While there are others, and they'll work, they don't need to be fast, and they don't need to be in the kernel. In our measurements, the IOAPIC, the PIC, and the PIT just don't get hammered that often. Just about everything through the IOAPIC is being routed to user space, is coming from user space anyway, in one way or another. It complicates the event FD signaling, but we have a solution for that as well. So the emulator is usually not perf critical either, at least in our measurements. I'm sure someone here has a workload that's going to dispute that. But if you move everything that's MMIO accessible into user space, then you're probably making a trip to user space anyway, for emulators. And then some MSRs are going to stay in the kernel. We haven't done that. We haven't worked that out yet. Yes?
I think IOAPIC is performance critical.
I agree. So what
Everything else is not.
OK, so what we're building is we're going to do, we're going to do IO event FD, but the event FD is going to actually send a posted interrupt instead. as opposed to sending instead of needing to do the interrupt routing in user space. Does that make sense? Or instead of doing the interrupt handling in the kernel, we're going to do most of the handling in user space and then keep a different IO event FD that we use to just send a posted interrupt to a virtual CPU. So basically same interface, except by the time it gets to the kernel, much more has been done. So what are the interfaces that we're building? So we created KVM create IRQ chip Lite. It allows access to the APIC page from user space. And then all the kernel does is enable the hardware-supported virtualization features. We may need to support non-self IPs for performance reasons, but we're not there. We haven't built enough to be sure of that yet. And if we do, it's going to be X2 APIC only, which means no instruction emulation in the kernel. There's this annoying set EOI exit bitmap. This is something to keep the IOAPIC in sync. And even with hardware-supported virtualization for EOIs, you need to occasionally exit to tell the IOAPIC about it, so we had to wire that through the kernel. KVM set exit on emulation. That tells user space to do the emulation. We haven't written that one yet. And then KVM set MSR exit bitmap. The interface that we're using right now, although this certainly could change, is we're just copying the same structure that Intel uses when it sets the MSR bitmap for hardware. And then we use an expanded KVM run structure to sort of plumb out more information about that's needed for emulation and the IRQ chip, the APIC access page, or the APIC page, not the access page. All right. Are there any questions or comments on what I did wrong?
I'm just wondering why a self-IPI is so much more important than non-self-IPI.
I don't know. Self-IPIs are easy to do because the hardware supports self-IPIs in Ivy Bridge, so it will do a self-IPI without a VM exit. So it's easy for us to get that.
It's back to VMS. So yeah. Windows. All right. Yeah. Windows does a lot of stuff.
On a bad day, you get a million hits on the API second potentially. So.
Okay. Any other questions?
Are those things, do you use them in production use, or is it just for...
We're not using this in production yet, hopefully soon. The goal is to have it by within 1 or 2 quarters on some of our production usage of KVM. We use KVM in a lot of different places. Our first target isn't Google Compute Engine, it's another Google product, but it should be 1 to 2 quarters. Go ahead, over here first.
What about vHostNet?
What about what?
vHostNet.
We don't use vHostNet. That's where where it goes directly to the host kernel driver, right? Yeah, I mean, so a decision was made before I even worked at Google that was probably too risky from a security point of view.
On this night, you also try to have some of these APIs with APIs and user space on the kernel, and I found it quite hard to keep all the information in sync. Doesn't the communication between kernel and user space, when you share information, also give an attack vector for security issues?
So essentially, by making the host ring 0 to ring 3 interface more complicated, yes, we do create attack vectors from host ring 3 to host ring 0. I think they're not all that complicated. I think they're not too bad. And that's a threat that I consider much, much less, right? So from my point of view, and maybe I'm going to get flamed for saying this, the Linux kernel attack surface is enormous. And there's kind of a good faith effort to find bugs there, but that's kind of how I see our effort to sort of keep vulnerabilities from host ring 0 to ring 3, or for host ring 3 to ring 0. But I suspect if somebody spent a few months and really wanted to find one, they'd find one. I'm sure of it. That's not how I feel about KVM. I think the level of effort that we put in, makes it pretty unlikely that somebody's going to find one, or it makes it very hard for somebody to find one, from after what we've put in. I think, I've been looking for vulnerabilities for probably 10 years. I don't think I've ever seen a project that's had more engineer hours per line of code from a security point of view.
Where can I find your patches?
They're coming. They're coming.
So IOAPIC had a proposal a few years ago to move everything but the local APIC emulation virtualization down to user space because, like,
okay.
speaking, the local APIC is really part of the CPU, and so like while you can move some of it down to user space, architecturally I think it makes more sense to keep the local APIC in the kernel, and then you also have a pretty well-defined interface between the user space and the kernel, and the protocol between the IOAPIC and the local APICs. I think that's pretty well documented. So.
Yeah, so
Okay, I didn't realize there was a proposal to do that. But
yeah, one thing that we actually saw a lot in real benchmarks is like if you run with dynamic ticks, the scheduler timer, setting the scheduler timer takes a lot of CPU percentage.
Oh, okay.
And if you move that in the user space, it will be much worse. So
Okay.
the LAPIC timer probably should also stay. Even
Okay.
though it's not accelerating. Because you use HR timers
Yeah.
and inject the internet directly.
Yeah, well, so that's something that doesn't really have much of an attack surface. I mean, it has some, although one of the vulnerabilities was in that. So I shouldn't say that, but okay. Yeah, well, so one of the things that I think made us more comfortable sort of splitting on his point about that it's sort of weird to have the APIC half in one and half in the other, is that you kind of already have that now with the hardware-supported virtualization. Like, so the hardware can already sort of write to some of those memory addresses that the kernel is expecting. So there's already kind of that shared model, and it seems to be working pretty well. And I think the way we share it is modeled on how it's shared between the hypervisor and the actual hardware.
So do you have a specific list? How is the virtual machine created? Can the user influence how it, what devices are present, or is that a fixed set that you are qualifying?
What do you mean?
Devices was the biggest piece of the cake. What type of devices do you allow, and when there are lots of devices you can?
So the cake I showed was, so when I say KVM, I'm definitely not talking about QEMU, I'm just talking about what's in the kernel. So that pie was the 6 of those were from the kernel, the 4 devices that are in the kernel, which are the PIC, the PIT, the IOAPIC, and the APIC.
So when you say user level, you basically move the code to the QEMU or somewhere else?
It'll need a user space user. We don't use QEMU at Google. We use something else. Okay, so but we recognize to get it upstream, we'll need to get something into QEMU or KVM tool.
So the current code is not in the QEMU?
No, but patches for KVM are coming. We're still working on this. I just wanted to, this is what we're doing internally. There will be patches, I promise. All right. Thank you very much.